Hello everyone, and welcome back. Today we're going to continue our exploration of linear programming and talk about the duality theory for linear programs. So let's begin just with a quick review of the main idea of linear programming. So we usually are given some objective function f of x, which has usually two or more variables. In this case, it's going to have x1, x2, and x3, and we want to optimize this function. And that's typically either a maximization or a minimization problem. And then we usually have some constraints, typically at least two, but you could have one or you can have no constraints whatsoever, which are given to be these inequalities. You could, of course, have greater than or equal to or equal to, but typically they're closed half spaces, not open half spaces, i.e. strictly less than or strictly greater than. And then we have our restrictions on our particular variables, x1, x2, and x3. And of course, you can have some variables that are not restricted at all. So we actually already discussed how to solve linear programming problems by hand, and the method that we used was referred to as the simplex method. So if you do know the simplex method, or maybe you want to practice your maybe MATLAB optimization toolbox approach, maybe you can go ahead and try to solve this particular linear program. But once you actually go through the solution process, then you should be able to show that the optimal solution is going to be equal to, so our vectors are going to be x1, x2, x3, and we're also going to have some slack variables s1, s2, and s3, and one can show that the optimal solution for these particular values is going to be equal to 12, 42, 0, 0, 44, and 0. That is, the basic variables that generate the optimal solution are going to be x1, x2, and s2 with non-basic variables x3, s1, and s3. But if you don't know about basic and non-basic variables and basic and non-basic feasible solutions, definitely check out our discussion where we actually go into detail a little bit about the theory about those particular concepts. So of course, once we have our particular optimal solution x star, then we can evaluate that particular objective function, and I'm actually going to be representing this objective function today as f sub px, and you'll see why I wanted to note this a little bit more detailed in just a moment. So once you plug in 12, 42, 0, 0, 44, and 0 into that optimal function, you can see that that gives us a value of 246, and you can try all the other basic feasible solutions and notice that you cannot actually generate a value bigger than that. And if you have some 3D or 4D software for graphing, you can also verify that graphically. Now, the main question that we want to talk about today is the following. So how can we be sure that this x star and fpx star are correct? So we're going to be talking about a method that we can actually use to verify that this is indeed the optimal solution and the optimal value of our objective functional. So to begin our discussion of what is called duality theory, I need to introduce two concepts. The first is known as the primal problem, and this is where that p that I introduced into our objective function actually comes from. So we're actually going to have two objective functions. The first objective function is going to be associated to the primal problem, which we're going to be denoting by f sub p. So in the primal problem, our goal is to maximize, and it doesn't have to be maximized, it could be minimized, but we'll discuss the variations in just a moment. But let's assume our goal is to maximize the functional fx, which is represented as ctx, and we're going to call this functional f sub p, subject to the following constraints. Ax is less than or equal to b with x greater than or equal to 0. So this, for example, can be our primal problem, and as you already know, just like we can write any linear program in standard form, you can also write any linear program in this particular form as well. But just as a side note, a primal problem doesn't have to be in this particular structure, i.e. a maximization with a less than or equal to constraint with all variables defined to be non-negative. It could be others, but this is just sort of a foundation of what we're actually going to be talking about, because we know we can always write it in this form, so you can technically only memorize one version of this what we call duality problem from this perspective if you desire. So there's actually another problem that is very, very closely related to the primal problem, where the primal is usually the primary problem that we're trying to solve, and that is what is called the dual problem. So D-U-A-L problem. So the dual problem. And we're going to be usually representing the dual problem as D and the primal problem as P. So the dual problem for this particular primal problem, so primal and dual problems come in pairs. So if this is your primal problem, the associated dual problem is going to be the minimization of BT psi, so another variable psi, not necessarily, actually not x, subject to, subject to the following constraints. A transpose psi is greater than or equal to C, where psi is greater than or equal to 0. Okay, now notice that I'm using B, T, and A, or B, C, and A in both of these problems, and that is the same exact C, same exact B, and same exact A that I'm mentioning here. The only difference is I have primal variables represented by X and dual variables represented by psi. Okay, so keep in mind that for our particular problem, A was a 3 by 3 in our initial AX is less than or equal to B problem. Once you take the transpose of a 3 by 3, that's also a 3 by 3. But in the case that A, for example, is a for example, a 5 by 3, A transpose will be a 3 by 5. So it's not necessarily going to be the same exact matrix size when you transpose it. So technically speaking, these problems will look, at least on the surface, completely different. And of course, notice that here, this is C transpose X, and this is B transpose psi. So the B replaces C, and C replaces B when you switch from the primal to the dual problem. So if we go back to our problem that I specified right here, this particular, maximize this functional subject to these 4 or 6 constraints, what would be the dual problem for that particular primal problem? So if that is the case, if we start off with a maximization problem, that means the dual problem will turn into a minimization problem. So our goal is going to be to minimize the dual functional fd, and this is going to be a function of psi. So remember our coefficients from our previous problem. Our previous coefficients in our matrix was 54, 20, and 30. So our B's are going to become our C's in our objective function, and our C's are going to become our B's in our constraint matrix. So 54, 20, and 30 are going to be the coefficients of psi1, psi2, and psi3. So let's just write that out. So that's going to come out to 54 psi1 plus 20 psi 2 plus 30 psi 3, and it's possible that we may need some slack variables if we desire to write the dual in standard form, for example. Subject to, so now we're going to be taking the transpose of our coefficients. So in our first row we had 1, 1, and 1. That's going to be our first column. Then we're going to have 5, minus 2, 1 in our second column. And then we're going to have minus 1, 1, 5 in our third column. Okay? And those variables are going to be represented by psi 1, psi 2, and psi 3. And the coefficients 3, 5, and 1 are going to be in our B column. And since we have everything being in less than or equal to form, we're going to have greater than or equal to form, greater than or equal to form for our dual problem. So this is going to be subject to psi 1 plus 5 psi 2 minus psi 3 is greater than or equal to 3. Psi 1 minus 2 psi 2 plus psi 3 is greater than or equal to 5. Psi 1 plus psi 2 plus 5 psi 3 is greater than or equal to 1, with psi 1, psi 2, and psi 3 all being greater than or equal to 0. So given our original primal problem, this would be the equivalent dual problem for that. So our goal here is to minimize this. Now one can ask, well, what is the relationship between a primal and a dual problem? You'll see in just a moment. But nonetheless, we can actually solve this in our normal way, right? Because, this is a minimization problem. So if I need to switch this into standard form, I don't have to change that. We have 3 greater than or equal to variables, so we would have to introduce 3 surplus variables. So you're going to have a minus S1, a minus S2, and a minus S3 in your coefficient matrix. And then you're going to have coefficients of 0, 0, and 0 in our objective function. And of course, you're going to have our surplus variables there, and pretty much an opposite identity matrix thrown into your coefficient matrix appended to this already 3 by 3 matrix, and our B's would of course be 3, 5, and 1, which is our C's from our original matrix. Right, so what is that going to give us? So if we actually go ahead and solve this, for example, via the simplex method, and some people actually refer to this as the dual simplex method because we're performing the simplex method on the dual problem, then you can actually show that psi star, the optimal solution of this dual problem, is actually going to be given by, so we're going to have variables psi1, psi2, psi3, surplus variables s1, S2, and S3. And the optimal solution is going to come out to 4, 0, 1, 0, 0, and 8, which is not the same exact solution as previously mentioned before. Keep in mind, these are different variables. But there's going to be one thing that is very, very interesting. So if we evaluate the objective function for the dual problem, which is f sub d, and evaluate this at f star, we're going to get 246. Now, that number should look familiar because that is precisely the same as the primal problem objective function evaluated at its optimal solution. Now, is that by chance, or is there really something truly behind that, right? And we will introduce a theorem that actually encapsulates this beautiful, beautiful property. But before I want to get into the theoretical aspects, I just want to make a little table that sort of summarizes the relationships between the primal and the dual problem, just in case you want to summarize this little transformation. Like how can you get the dual problem for any linear program, right? So for example, we usually have our cost vector, which is C in the primal problem, and then we have, for example, our constraint coefficients, which is typically represented by A in the original problem. And then we have our restriction, or our constraint vector, let's call it. Constraint vector, which is usually B. So in the primal problem, P, and then we're going to look at this in the dual problem, D, what do we have? So we usually call the cost vector C, the constraint coefficients in A, and the constraint vector B. So remember, for the dual problem, C and B switch positions, so B turns into the cost vector, C turns into the constraint vector, and A transpose turns into the constraint coefficient matrix. And the variables, we usually represent this by X, and this by psi. Some people will use some other letters that are maybe easier to write. I've seen pi, I've seen like chi, I've seen y even. But I think psi and x typically go better together anyway, at least in the functional analysis perspective. Also, if you have some different types of problems, for example, let us assume you have the problem ax is less than or equal to b, with x greater than or equal to 0, then this turns into, in the dual world, what does that turn into? Well, that's precisely the same thing as our problem that we just saw. That's going to turn into A transpose psi is greater than or equal to z, with psi greater than or equal to 0. And there's one other problem that also we often encounter, and that's the standard form approach of the primal problem. So if we have, for example, ax is equal to b with x is greater than or equal to 0, this is going to be equivalent to solving A transpose psi is less than or equal to c with psi unrestricted. So you would have to introduce, for example, a psi plus and a psi minus for each of those unrestricted variables. I'm not going to go into the proof of this one, but I'll leave it for you to sort of verify why that actually is going to be the dual of that particular linear program. Now let us get into some of the theoretical aspects associated to the duality of linear programs. The first might not be of interest to the practical user for linear programming, but if you're familiar with some of the theoretical aspects associated to dual spaces for like vector spaces and so on, then this theorem should look very, very familiar to you, and if not, that's okay. But let's assume that D is the dual of the program P, and what if we take the dual of the dual, right? So if you find the dual of a primal program P, and then you find the dual of that dual program, you actually will get the original primal linear program P. So the dual sort of cancels out with itself. If you think about like transpositions of matrices from linear algebra, it sort of has that same type of structure. So if you take the transpose of a matrix, you get the original matrix back again. Some people will even write the dual as a little prime. So if you have the prime of the prime, then that's technically equal to the original A, where prime represents dual in this particular structure. That's pretty much what's going on here. Pretty much dual, if you treat it as an operator of a linear program, it sort of cancels itself out. I'm not going to go ahead and prove it here since it doesn't really apply to the conversation at hand, but if you want to try and do so for the general case, definitely feel free to do so. Now this next theorem is going to be of importance to us, and this is called the weak duality theorem. So the weak duality theorem, and yes, there's going to be a strong duality theorem as well. So what we're going to do is we're going to first let x belong to the feasible region of the primal program, and we're also going to let psi be an element of the feasible region for the dual program. Then the following inequality always holds. Ctx is always going to be less than bt psi. That's always going to be the case. Right? So if you do the cost function for x and the cost function for psi, it will always satisfy this particular linear inequality. So if you think about this from the practical perspective, usually we're trying to maximize that particular functional, and usually we're trying to minimize that particular functional, or vice versa, right? So if that is the particular case, this value is going to be maximized at the same place that function is actually going to be minimized, right? And that will lead into that quote-unquote consequence that we got for our numerical example before, where even though the solutions x and psi star were different, they actually produce the same exact value, and that's going to actually lead into the main theorem of the duality theory for linear programs. But let's first off start off by proving this weak duality theorem. All right, let's see if we can do this. So proof. So what we're going to do is we're actually going to look at this in summation notation form. So we can represent, for example, Ctx as the summation from j is equal to 1 to n of Cj xj. So we know that this is actually going to be less than or equal to the summation from j is equal to 1 to n of, well, remember what Cj is actually equal to. That's actually the same thing as A transpose psi, the jth row, times xj. So I've actually just left this xj the same. Now keep in mind, why is that the case? Keep in mind for our dual linear program, we know that A transpose psi is greater than or equal to C. That's the constraint form for the dual version of the primal program P, right? So if that is the case, if we sort of write this version in summation notation, then this is going to be equal to the sum from j is equal to 1 to m. Let's use or k for the index of that particular structure. That's going to be the sum from k is equal to 1, and that's going to be to m, not m. And this is going to be a kj times psi k. And then that's going to be represented by xj. Keep in mind now, xkj, psi k, and xj are all numbers. Well, not all numbers. Xj is a particular, no, those are all numbers. So what does this case? So if this is the case, I can actually rearrange these summations a little bit. So that's going to be equal to the sum from k is equal to 1 to m of the sum from j is equal to 1 to n, and we can represent this, well, since these are numbers, we can exchange them. So this is going to be equal to akj times xj, and then times psi k. And now we should know what this is. That's associated to AX, the kth row. So if that's the case, then we can write this as the sum from k is equal to 1 to n of the kth row of AX times psi k. And we know that the kth row of AX is actually equal to BK because we know that AK or AX is less than or equal to B. So if we look at the kth row, that's also going to be the case. So this is going to be equal to or less than or equal to the sum from k is equal to 1 to n of BK psi k, which we know is the same thing as writing B transpose psi. So if we look at these inequalities, we have B transpose psi on the right-hand side, and we have C transpose X on the left-hand side. So we've proven that CTX is less than or equal to BT psi for all X and psi and their associated feasible regions. Now, I need to make sure that you understand one thing in this notation. So note here that X in FP and psi in FD are arbitrary. So if you choose any X and any psi in their appropriate feasible regions, then this inequality always is going to hold true. Now the next theorem that we're going to look at today is actually one of the more important ones. Yes, the weak duality theorem is very important and we're going to use it here, but this problem pretty much enlightens what was going on with that example that we started off with today. And it says this: if x star is a particular solution in the feasible region of the primal problem, and psi star is a particular feasible solution in the dual problem, and if CTX star and BT psi star are equal to each other, that is the objective function evaluated at x star for the primal, and the objective function for the dual problem evaluated at psi star are equal to each other, i.e. equal to the same optimal value. The maximum of one equals the minimum of the other. Then psi star and x star, those particular feasible solutions, are actually the optimal solutions of those primal and dual problems. So, if you can find an x star for the primal and a psi star for the dual, such that CTX star is equal to BT psi star, you've actually found the optimal solutions for both the primal and the dual. That's pretty much what we're going on here. So, how are we going to go about proving this? So, proof. So, from the weak duality theorem, we know what? So we know that CTX is going to be less than or equal to BT psi for all X in FP and for all psi in FD. We know that's always going to be true. So if that's always going to be true, we can choose a particular psi. So choose psi to be equal to psi star. Since it's true for all, I can choose a particular one. So if that's the case, that means CTX is going to be less than or equal to BT psi star. By our assumptions, we know that BT psi star is going to be equal to CTX star. So that means we have CTX is less than or equal to CTX star. So that means if we look at this from the objective point of view, that means f of x is going to be less than or equal to f of x star, and keep in mind this is the primal objective function, and this is going to be true for all x in the feasible region of P. Right? Notice that we're comparing the same exact functionals, fp to fp, and this is a particular number, and this is a set of values. So that means x star is an upper bound for all of the values for which fp can take, provided that this number x star, of course, exists. So if this is true and x star of course is a particular value in fp, that means what is true about x star. So if we're trying to maximize f of p and fp of x star is greater than or equal to all the values that fpx can take, that means that x star is an optimal solution for our primal problem p. Now, what does that say about psi star? So let's see if we can build an argument for that. So we know that B transpose psi star is equal to C transpose X star, right? And we know that C transpose X star is less than or equal to B transpose psi for all psi in the feasible region of the dual problem, right? So this is a particular subset of the weak duality theorem, because we know CTX is less than or equal to BT psi, So we can choose a particular x and particular x star, and that is also going to satisfy. But if we look at the outer inequality here, we have that bt psi star is less than or equal to bt psi for all psi in the feasible region of D. And if we write that in functional form, that's the same as fd of psi star is less than or equal to f psi for all psi in fd. So what does that mean? Well, keep in mind if we're trying to maximize FP, that means we're trying to minimize FD. And what we have here is that FD psi star is a lower bound for all of the values for which FD can take. So if that is the case, and psi star, provided that it does exist, is in the feasible region FD, that means what is so true about psi star? That means psi star is an optimal value of the dual problem of D, which gives us both directions of what we are trying to prove. So for our particular example, remember that we had that FP of the X star that we obtained was equal to 246, and that was also equal to FD of psi star. So if we found those particular values, psi star and X star, and they give us the same exact functional value when we plug them in, that means this is the optimal solution for P, and that is the optimal solution for D. We are guaranteed that that is the case. Now, what if they are different, right? So we at least know from the weak duality theorem that Fp of x is less than or equal to Fd of psi for all x in Fp and psi and FD. We already know that that is the case. So when they are not equal to each other, i.e. when x and psi are not the optimal solution, and we look at, for example, the difference, well, we already know that FD is always greater than FP. So if we look at the difference FD psi minus FPX, so this is always going to be greater than or equal to 0, right? So this difference here is what is commonly referred to as the duality gap for the solution pair x psi, right? And one, of course, can prove as a corollary from these theorems that the duality gap, FD psi minus FPX, is always greater than or equal to 0 for all feasible solutions x in FP and psi in FD. For the last few theorems, we've been assuming that an optimal solution for P or D exists, right? So one could show that if P has an optimal solution, D also has an optimal solution as well, and I'll leave it to you to try and prove that. But what if an optimal solution for P does not exist? Well, from the fundamental theorem of linear programming, we know that if we have a set of, for example, basic feasible solutions, the optimal solution is either one of them or the feasible region is unbounded, right? So what does that mean for the dual problem? So if P is unbounded, then D actually is inconsistent, i.e. there's no solution in the feasible region, i.e. the feasible region is the empty set. So how do we actually go about proving this interesting result? Right? So we're actually going to go ahead and prove this by a contradiction. So suppose that P is unbounded and, on the contrary, that D is consistent. So if D is consistent, then that means that there exists at least one number, let's call it psi star, that belongs to the feasible region of D such that the following inequality holds. In particular, CTX is going to be less than or equal to BT psi dash. And this is going to be true for all x in the feasible region of P. But what exactly does this mean? So this means that any x in the feasible region is bounded above. So if that is true, that means that FP is bounded. But that contradicts the assumption that we had there, right? So that's a contradiction. So it's a contradiction to our assumption, therefore by logic that means if P is unbounded, that means our contrary assumption is actually false, right? So that means if P is unbounded, then D is inconsistent. Right? Now let's think about this from the other direction. So theorem 5. If D is unbounded, then what can you guess about P, the primal problem? So one can show that P is inconsistent. So if the dual of a primal problem is unbounded, then you should be able to show that the primal problem does not have any feasible solutions. And with those, and of course you can sort of combine them into the same one if you want, let's actually go ahead and state this last theorem of the day, and this is called the strong duality theorem. And it says this: if P has an optimal solution, x star, and let's of course assume that it's finite, that we usually do, then there exists a psi star that is finite for the dual problem, and fp x star is less than or equal to fd psi star, which we've pretty much proved all the little elements of this particular thing, but this pretty much throws it all together. So that is, if you can find a primal problem or find the optimal solution of a primal problem, that means there always exists an optimal solution for the dual problem, and the weak duality theorem will always satisfy that particular objective function comparison. So those are the basic theorems and ideas and application of the duality theorem for linear programs, and can also be viewed as pretty much a certificate of authenticity for the solution that you obtain for the optimal solution for a primal problem. So I hope you enjoyed, and I'll see you in the next video. Take care.